All right, it's 7:30 Pacific time, November 26, 2025. My name is Timur. I'd like to welcome everybody to our Mat3ra webinar series. We have Seth with me on the line.
Hello.
Lately, we've been working on the open source code base that allows for design and development of two-dimensional materials. And today, we'd like to showcase some of its functionality to you. Let's get to the next slide, please. Here you can see some of the arrangements that are possible with the help of Mat3ra. You can design realistic atomic arrangements, including monolayers, bilayers, surfaces, interfaces. And as you will learn today, you can include things like surface defects, point defects, grain boundaries, and so on. This is the third webinar in the series, and today we're going to be focusing on designing structures with defects. Next slide, please. Before we start, this is the set of rules for our engagement. The goal of this webinar is to make you comfortable and familiar with Mat3ra stack. Every participant should be a registered user with Mat3ra, but you should be able to use the open source packages even if you are not. We will share this presentation with you on YouTube, and right now we're recording this as full disclosure. Let's go to the next slide. If you have questions at any point during this presentation, please don't hesitate to ask. We have both Q&A and specific chat available as part of Zoom application. We'll answer all the questions at the end. Next slide. All right, so without further ado, Seth, please, the floor is yours.
Greetings, everybody, and welcome to Mat3ra webinar series. My name is Seth, and I'm going to present you Python package for the design of 2D materials. First, we're going to look over the presentation, which will give you an overview of our approach, and then we're going to get to hands-on experience. And today is part 3 series. We're focusing on point defects, surface defects, and grain boundaries. One of the challenges in material science today is that materials used to train machine learning models are structures of ideal 3D crystals, while real-world applications require structures that are more complex, such as defects, surfaces, or interfaces. In order to do that, we needed a way to generate such materials. We created an easy-to-use Python framework for the design of 2D materials. Our approach has well-defined data structures that help organize information in a database and make it easier to build machine learning models later. And we demonstrate the application of our approach with a set of Jupyter notebooks that can be run in any browser. We primarily focus on 2D materials and interfaces because we believe this is the area of increased interest, which is important for electronics and batteries research, and important processes occur at the interfaces. Here you can see some examples. For example, passivated grain boundary, intercalation of the interface, and other forms of interfaces. Our implementation includes 5 components. First one is data standards, a set of entities and ontologies structured in a categorized matter, stored as a data structures in JSON schema format, and this is the Mat3ra SC package. Next one is the commonly used examples data, which has examples of the data of the entities adhering to the data standards from the first point, and it's stored inside of the Mat3ra stand data package. Third one is the generic code base, Mat3ra code package, that has implementation for all of the entities to work inside of Python or JavaScript. Fourth is the specific code base, which has, for example, for the materials design, it's a Mat3ra made package, and it has all of the necessary tools to create and analyze materials inside of Python or JavaScript. And the fifth one is the code usage examples stored in Mat3ra API examples package, which has a collection of Jupyter notebooks that show how to use the approach and showcase how to use the Mat3ra made package. We're going to be focusing primarily on the 4th and 5th today. I'll repeat I'll show in more detail all of the 5 components. So the first one is the Mat3ra ASI package, available on GitHub and PyPI. It defines, for materials, it defines schemas for their structure, common physical concepts, and operations. So all of the definitions for surfaces, point defects, etc., are defined here. Then next one is the examples of the data. For materials, we have a list of most commonly used materials, and they are named in such a way that it represents the categorization they adhere to. And the structure is available, and this is Mat3ra Standard has the materials structure information, and it can be used as a standalone database to fetch some of the materials. Next one is Mat3ra made package, where it's also available on GitHub and PyPI, where we implement material instances and tools for transformations inside of Python. It has basic definitions for concepts such as material, lattice, basis, and cell, as well as a set of tools and analyzers to build more complicated structures. And the last step is a set of Jupyter notebooks demonstrating how to use the Mat3ra made package in a self-documenting manner. So each notebook showcases describes what result we want to achieve, has a set of parameters for the material structure that you want to create, and it shows how to use Mat3ra made package functions from it to make it easier to understand how to use it. It also can be used as a practical tool where you can just use the notebook as it is, just changing some of the parameters and construct structures in your day-to-day life. And also they are easy to collaborate because you can easily share, create your own notebooks, and store the way that you constructed the material for later reproduction. And also the last stage is making sure that this functionality is available to the user. We provide ability to use this to use Mat3ra made and the Jupyter notebooks inside of the familiar environments such as Jupyter Lab, Anaconda, VS Code, or with the help of PyDiet, which is the Python runtime in a web browser. We also allow to run any notebook just in your web browser, where you don't need to set up anything. You can just open up Jupyter Lite notebook from a website, from a link, or within the platform, or within the Materials Designer application, and run everything without the need to set up the whole environment. And it allows to run any pure Python package, as well as we set it up to allow for usage with Mat3ra made, Pymogen, and ASE. We're going to be using this UI today. Let's look over the implementation details for our approach. Let's say we want to create some structure. We split the approach into 3 categories, where you configure a target material, then you transform it, and as a result, you get material with metadata. For example, if you want to create a slab, we want to start with the bulk material, provide parameters of the target structure, for example, Miller indices, thickness, vacuum, thickness, etc. Then we would take a builder, slab builder in this case. Builder applied to the configuration yields result, which is a material, a surface in this case, with the metadata of the transformation stored for provenance. Sometimes you might not know all of the parameters beforehand, and in that case, we need to make it. We need to create we need to split into three steps where we define, refine, and build. For example, if you want to create an interface, you need to create two slabs and match them so that they are commensurate. You don't know the supercell for the matching, so that's why you need a refine step. So we would define two slab configurations with each respective bulks and mirror indices and thickness. Then we would use some analyzer, some interface strain analyzer. For example, we heavily use the ZSL Zor-McGill lattice analyzer. And as a result, we would get multiple interface configurations that are ranked by size of the overall unit cell and by strain. And depending on your needs, you might select the most optimal structure for your use case, and then apply interface builder to the interface configuration that you selected. And as a result, you get the final interface with all the metadata and the process stored. To make it easier to find specific material transformation, we use categorization that you can see here, where we split materials into domains. For example, pristine structure, which is a simple material such as just ideal crystal or a slab. Next one is compound pristine structures, which combines multiple pristine materials, for example, in the interface. Then we have domain of defective structures, which is defects such as interstitial or substitutional point defects. And at the end we have, and here we also have the process structures, which is mostly passivated or perturbated structures. Then each domain is divided by dimensionality. And then later you have the final category. Some of the categories have different variants. For example, for the interface, you might have ZSL or commensurate lattice approach, depending on how you achieved this structure. For today, we're going to be focusing on defective structures mostly, only on defective structures. For example, we're going to have two examples of 0G point defect structures. One example of linear grain boundary, and three examples of surface defects. Today, we're going to be looking at materials designer application and import materials from Stendata. We're going to be using Jupyter Light transformation inside of materials designer to create a set of materials. Substitution in gallium nitride, vacancy point defect in graphene. For surface defects, going to be Adatom and island surface on titanium nitride surface, and plain grain boundary in copper and linear grain boundary in hexagonal boron nitride. Let's start with the first example, graphene vacancies. We want to start with the graphene monolayer and create a supercell with the vacancy in it. First, we'll start by importing material. For example, if we running it inside of script, we get the Stendata materials database and get by the name first match graphene, and then we need to create a class that we can operate upon. So we use material from made and create a material from config, and then all of the functionalities available to operate on this material. Next one, we'll specify the supercell that we want to create. Here, I'm just showing what functions will look like. You don't need to remember them because every notebook already has the examples of it. So you just need to open correct notebook. Here, I'm just making you familiar with the functions that we're using. So we would use supercell, create supercell to create a supercell. And then we would need to get a coordinate that we want to replace. So we can open it inside of materials designer viewer, select measurement, copy distances, and click on the atom that we want to replace, and that will copy us the coordinate in Cartesian coordinates to the clipboard, which we can later use in the setup for the defect. So for point defect is going to be, we would be using the point defect dictionary class. We allow for generation of multiple defects at once, so they are passed as an array. But we for now just have one defect. We would specify the type, vacancy, pass the coordinate. Element we can omit for the vacancies is going to be ignored. And placement method, here we would select the closest site, which will resolve this coordinate to the closest site that is available. It's generally better to use the closest site resolution if you want to remove the specific atom. And we would also set the use Cartesian coordinates flag to true, because by default we use crystal coordinates for the functions, but here we want to specify it as a Cartesian one. And then we would use the create multiple defects helper function, pass the supercell material that we created, and pass the defect dictionaries to generate a structure. So let's go to the materials designer Mat3ra.com to showcase it. Also, this functionality is available inside of the application, inside of the platform. If we go to materials and create material, we have the same materials designer application. So we want to go to input, output, import from data to import the graphene material. Search for graphene 2D monolayer. That's the materials coming from data. Submit, and we see it in the sidebar materials, but it's present here. Let me toggle bonds so that we can easily see it later. Okay, now we want to create a supercell and measure and get the coordinate that we want to replace. So we can create a supercell, get to the measurement, copy distance, and let's remove some atom. We have the coordinate copied in the clipboard as an array. So now we can go to advanced Jupyter Light transformation to open the Jupyter Light transformation window. Here we present it with the notebooks, Jupyter Light notebooks. And the first one is the introduction notebook. It always opens the first one, where you can see all of the notebooks named and they categorized, so you can search for the correct one. Today we want to create defects, so we would scroll down to defects and find point defects, vacancy, substitution, interstitial. We click that and you can see that it's opened here. Okay, we want to select the correct material to which is graphene. Okay, to work with it. Since we already created a supercell, we don't need to provide additional supercell here. We'll just use the unary one. For defect, we just need a vacancy, so we can remove all of this and pass the coordinate. And again, use Cartesian we set use Cartesian coordinates to true to tell how to resolve this coordinate. Then we would go to run all cells. This will install all the necessary packages, upload material from selected materials from the sidebar materials into the notebook under the materials variable. We will preview the structure, and then here we will see all of the defects, point defects that we will apply to it. So it's, in case you have multiple defects, it's nice to see all of the settings here. And as a result, we create multiple defects. We use create multiple defects function to create to apply all the defects, and we, as a result, get graphene with the missing atom. But so we don't see it here, but the metadata stores the information about the vacancy, so it can be retrieved later, so that we know that this is a vacancy. Next one is example of magnesium substitution in gallium nitride. We want to start with gallium nitride bulk material and add and substitute for magnesium atom. Again, we will import material from some data. Then we want to specify the supercell matrix that we want to get. And for defect and fix, we provide type substitution. We set the coordinate, for example, in crystal coordinates in this case, set the element and the placement method. And then we're using create multiple defects function, the same one, and create this defect. Yeah. So again, import from stan data, gallium nitride. Advanced Jupyter-like transformation. We'll select the gallium nitride and scroll down to the same defects, point defects notebook that we had. Again, we didn't save, so it restored to the original version. If we delete a notebook, it will download the latest version, so it will refresh basically. Okay, here we want to just select the substitution, provide the crystal coordinates and the element. And again, supercell, I think we wanted to have it factor of 2. If we run all cells, we would get the same, we would get the structure. So again, since we closed and reopened the Jupyter-Lite again, we need to install the packages inside of this notebook. If you run it afterwards, it will skip the installation. So we just need it when you reopen the notebook. And we can see that the substitution defect was added. And again, all the metadata for the transformation is stored within the material. The next one is the example of Adatom on a titanium nitride slab. We starting with the titanium nitride bulk material and want to create a slab and place a titanium Adatom at the position of the next layer's crystal site. So we would import titanium nitride from some data. Then we would create a slab. We had in part 1 of these webinars, we discussed slab creation in more details. So we would create a slab with this function, providing Miller indices, number of layers, vacuum, and if it's orthogonal, C. For defects, we would use the Adatom defect dict class. We specify the type Adatom, provide the coordinate, 2D coordinate of the surface in crystal coordinates, and the distance from the topmost layer to the Adatom in angstroms and the element. For the placement method, here we go with new crystal site, which means all of the parameters that were provided here for the coordinate will be resolved to the closest crystal site of the next layer. We can also use the exact coordinate placement method to place the exact coordinate that we provide, or equidistant, which will find all of the atoms in the vicinity of this coordinate and then resolve to the one to the coordinate that is equal distant from all of the surface atoms. Then we use create multiple Adatom defects helper function, provide the slab, provide the defect dictionaries, and the placement method for all of them. And as a result, we'll get a structure. So input, output from some data, titanium nitrate. Then we'll go to advanced Jupyter-like transformation. Select the titanium nitrate. Yeah, but by the way, silicon is also always come up because it's a default material. So that's why we have it the first material when we open Materials Designer. Okay, now we presented with this introduction notebook. We want to scroll to Adatoms, so it's defects. So we'll see here defects, and it's a surface defect, Adatom defect on a slab. Notebook explains how to use it and which properties to provide. Now let's set to the element to be titanium. Again, we can create multiple defects at once. Placement method, new crystal site. Now the slab we are targeting is 001, and maybe let's have a thickness of 2. Same supercell matrix of 2. Okay, now we can run all cells and get the structure. Here again, we're installing the packages and getting the material. And here we're using the slab analyzer to get the terminations in case materials has multiple terminations. And then we use create slab with all the parameters to create a slab, which we'll preview shortly. And then we create defects with the help of by setting the defect dictionaries and with the help of create multiple Adatom defects. And as a result, we get the material with the Adatom. We can submit it. We specified the distance to be 1 angstrom, but if we actually measure distance, it's 2.1 angstroms because we set the resolution to be the next layer new crystal site. So this means the titanium was placed at the next layer's crystal site. Okay, next one is the island on titanium nitrate slab. Again, we start with the same material and we want to create island. Import material and then create a slab. In this case, it's going to be a bit larger. And then we want to create a slab. I want to create an island by filtering with the box coordinate condition. So we would select box coordinate condition that is this defined with the crystal coordinates inside of this large surface, and use create island to create the island defect. We would specify the number of added layers in number of unit cells. So for titanium nitrate, we have titanium and nitrogen forming 1 unit cell. So half of that will yield just thickness of one atom thick. And as a result, we'll get the structure. For this one, let's view the other option to open the Jupyter Light session is to go to the view and Jupyter Light session, which will open up the drawer that you can open and close. And it can be easier because it preserves all the progress. You don't need to close it. You can just scroll down and have all of the progress preserved. For this one, we're going to go to the specific examples and defect surface island titanium nitrate. This is where we reproduce a paper. So this is example of the paper where they had this structure, titanium nitrate with the island, and we want to reproduce it. So here we pre-define the parameters for the island creation, number of added layers, a shape parameter. It can be a box, it can be cylinder, prism, or other parameters that are available in the other forms to filter the material. We have slab parameters for the slab that we want to create, and if we run all cells, we'll download the packages. Then we're going to create slab from the titanium nitrate that we get from data, and we will create a target material by creating a coordinate condition, box coordinate condition in this case, with the shape parameters that were measured before, and create island with the helper function. And as a result, we should get a final structure. It says it's busy, so okay. So we have the supercell, and yeah, in this example, it also saves material to downloads material to the machine. And here we can just scroll this down and see the final result of the island. Next example is the planar grain boundary in copper. So we start with the copper bulk material, and we want to create a grain boundary of 001 and 011 copper. We're using to create the structure. We're using the same ZSL interface analyzer, so it's basically a creation of interface between the two materials. So we would import the material, then we want to pass all the parameters for the slabs, and for some material you need to get terminations. For copper it's not necessary, but in general you want to get the terminations that you want to select for each slab. Then we would use create grain boundary planar helper function, pass phase 1 material. You can also pass different materials for each phases in case there's some difference, some subtle difference between the two variants of the material. And then we select and then we specify the same slab parameters for both of the phases, as well as the gap and the translation in case we want to move the second phase along the gap, and property and parameters for the ZSL analyzer, so maximum area and tolerances. This will yield multiple multiple ZSL matches, and then we can select which match we want to get. And here we select one with the lowest strain and also the lowest strain, and then they are arranged to have lowest size as well. So, and as a result, we should get a grain boundary. Closed here. So let's import the copper. Go to advanced Jupyter-like transformation. We would select copper material here. Then scroll down to defects, planar defects, grain boundary in a 3D crystal. Again, it explains how to use the notebook. So phase millimeter indices 001, thickness in unit cells in atomic layers 2. This one for the second phase, interface gap, maximum area, and we can run all cells. To install the packages, import the material, visualize the original material, and then again find the terminations. Should be just one for copper. So here we pre-visualize for multiple terminations if there's multiple of them. Then we create a grain boundary with the help of the function that we saw before. Okay, so just the slab that we preview, and the grain boundary should be coming here shortly. Looks like I have some grain boundary from the previous run, but of this notebook. Let's see. Well, yeah, okay. Looks like I had some copper grain boundary of the previous run when I was running this. Let's see how it looks, because it takes some time for some reason. Maybe because we have others open. Well, okay, so grain boundary, it's a bit larger than I expected. So here we should see the 001 and 011 orientations, and they're labeled accordingly. Okay, let's go to the next one, which is linear grain boundary inside of hexagonal boron nitrate. So we start with the boron nitrate monolayer, and we want to create a commensurate interface that has some specific angle. In order to do that, we would get the boron nitrate from some data. Then we want to use the create grain boundary linear and pass the material, then the target angle, as well as the angle tolerance to narrow to allow for some change, some tolerance to find this angle, and then the max repetition, because the way it searches for the commensurate lattices, it tries to find all of the supercells, starting from all the supercells from 1 to 6, with values from 1 to 6, or any other repetition value that you have here. For the hexagonal, it'll get some of the pre-tabulated pre-tabulated value, so it should be fast. But for any arbitrary lattice type, it will take it will take longer. Provide the gap between the two atoms, that all of the atoms within between them will be removed, and the middle indices for the, in this case we just using the planar monolayers, so 0, 0, 1 and some vacuum, and as a result we should get the grain boundary. For this one, we again going to be using Jupyter Light Session Drawer as an example. Let's go to the specific examples and find the defect linear grain boundary. So 2D grain boundary inside of the boron nitrate. Again, here we reproducing the paper. It explains how the grain boundary is created, and here we have all the preset values. So for the search term for boron nitrate, the angle. Okay, here we have try to do this 17 2 degrees boundary gap. So if we just a second, let me reset. I think I was changing this notebook. Okay, there is. So I just deleted the notebook to reset it to the latest version. So yeah, that's the angle. That's the values that we want to create. So if you run all cells, we're installing the packages, then we're going to preview the material, and then create grain boundary with the from this material with the target angle as well as angle tolerance and repetition that we see. Also, it generates a lot of it searches for all of the materials, all of the possible combinations. So if we want to get just the first match and make it faster, we just set the return first match to true, which is set here. And we should get the result. Okay, this one takes. This one takes some time for the search. Maybe let's see if we have. Maybe I can reproduce it faster here. Let me. Okay. We did have the. Okay, it returned the structure to the. Okay, I think it ran and returned the structure to the main working space. So here we can see the grain boundary in the boron nitrate at the angle that was specified. So reproducing the reproducing the paper. Again, to have a close match, you need to we need to relax the structure so that atoms will move and fill up the gaps, but it should reproduce the same structure that we see here. I think this was the last example. And just to remind that we have notebooks for typical use cases that are available on jupyterlight.mat3ra.com or accessed from Materials Designer app, or from the platform where when you create a material, you would get when you're creating a new material on the platform, you can get you can open the Materials Designer application. So today we reviewed Mat3ra made Python framework and how it helps you create point defects, surface defects, and grain boundaries. We showed a set of Jupyter notebooks that provide real-world examples for the structures, and that it's available on jupyterlight.mat3ra.com or Materials Designer or the platform. All code is open source and available on GitHub and PyPI, and we welcome any contributions and suggestions.
All right, thank you, Seth, for the presentation. Now we're back to Timur here, and let's see if we have any questions in the chat or in the Q&A session. If you have any questions, right now is the time to ask. All right, I don't see any questions as of right now. Let me start the discussion with maybe showcasing how we can incorporate information from pre-existing structures, like with POSCA or CIF files. That's usually good to cover.
Yes, so for example, if you want to open some CIF file, we have a notebook for that in the other. So if we go to open the introduction notebook and go to the other, import data from files in AAC supported formats, we have here folder path that says specifies the folder, for example, files where we can drop some of the materials. For example, here I already have from some work the CIF files, but you would just go and drop some material in here. Then if we run all cells here, we should get all of the materials that we passed here. They should be reviewed and downloaded to the notebook and then passed to the Materials Designer. We can specify and filter the formats that we want to see. For example, if we provided the CIF, we would only get this one. So okay, it read the it read the materials successfully, and so it shows the helper comment of all of the formats that we can view. And again, this is the materials that we uploaded from the CIF POSCA files, and they were sent to the Materials Designer in the set materials function, and we should have them here in the sidebar materials list. Okay, this one is a interface that we have here, and beryllium.
All right, let me continue this discussion, maybe with covering how you can run these notebooks locally as well.
Yes, sure. As I mentioned before, we can run these notebooks in in any IDE that supports Python. So for example, if we we use PyCharm, this is the Mat3ra API examples package, where if we go to the materials designer, we see all of the notebooks that we had in the Jupyter Lite. So the specific examples that reproduce papers. So then we have here the list of all of the notebooks that are used to create some materials. So for example, the grain boundary crystal that we were working with, we can run the structure. So for example, by default, we should have some materials in the uploads folder. So if we run all cells here, for example, we should have the first material. So the nickel will be first from the uploads folder.
Anyway, I think we have demonstrated the point at this time. Let's talk a little bit about how do we proceed with simulating these materials. Right now, we just designed the structures, right? We need to do relaxation. We need to understand how these materials can be characterized.
Well, we can send these materials to the platform for the calculations. So in examples, we have the API folder where we can create, for example, if we go to material, we can create material and send it to the platform, or where we can schedule a job, for example, to find to get the job, to get the workflow and create a job. For example, here we reproduce the band gaps for twisted molybdenum disulfide, where we create a material first, create slabs, create the twisted interface, and then we would log into the platform using the authorization tokens, create a material, save the material that we created to your collection. Then we would run. Then we would get the band gaps workflow that we want to find. So the espresso band gap using the query. We would copy the workflow to our own account, and then we're going to create, have some adjustments to the model that we're using, and then we would run then we would submit the workflow. Create the workflow and then submit the job with this workflow and the material that we created, and as a result, we should get again, all those changing all the settings that we can, and as a result, we should get the band gaps there. If we run all cells, it'll probably take some time to run the calculation.
We don't have to do it right now, but yeah. This is going to be covered in one of the future episodes of Mat3ra 2D series. I just wanted to give a quick shout out, quick demonstration of what's going to be possible in the future. Otherwise, usually disorder is an important factor, especially when we deal with defects. How are we going to address a disorder?
Disorder as in
when we form an interface, there is usually a disordered layer, right? A layer that doesn't have crystalline symmetry, that is amorphous. something is
amorphous.
happening at the interface that we have to address.
Well, amorphous, we're going to create the amorphous functionality, so we don't have it right now for the amorphous material.
Yeah,
Well,
there are a
we can
couple of ways
use
that we can address it. One way is to try to introduce the amorphous layer with things like special quasi-random structures. So there is a way to simulate materials that will represent amorphous phase. And another way would be to try to use force fields to pre-relax the interfacial layer. And that's something that we have in works as well for the future. Okay, I think we have covered most of the items. I'm going to ask the audience one last time in case there was something you wanted us to cover. Any questions? If you want to raise your hand and ask them directly, you can do so as well. It looks like everything has been clear. No questions so far. With that, I'm going to thank everybody and thanks Seth. Everything that we recorded here will be on YouTube shortly, and we'll continue next month with another episode. Thanks, everybody.
Thank you.
Bye.